we have Dr. Tatjana Isakovic. Sorry if I'm pronouncing your name wrong.
It
And
is okay. It is
yeah,
good.
and she's a professor at University of Ljubljana, Slovenia.
Ljubljana, yeah,
Yeah, sorry again. And she'll be
difficult
talking
to
about,
pronounce.
yeah, today she'll be talking about modeling of reinforced concrete walls using force displacement MVLEM methods. And thank you for your time. And yeah, it's all yours now.
Thank you that you invite me, and I have the opportunity to present this model, this element, which was developed at the University of Ljubljana. So let's start. So as it was already introduced, I'm going to talk about the multiple vertical line element model for reinforced concrete walls, which was developed at the University of Ljubljana. It is not the element which is also already included into the OpenSys, but a different kind of element, and it is available in the local versions of the OpenSys in Ljubljana. And it can be used, first of all, for modeling, for the analysis of seismic or cyclic response of reinforced concrete walls. It is actually a kind of macro model. It is a beam column element. So this is an example of some specimen that we recently tested. And we already performed also some analysis. And each pier was modeled with such a kind of beam column elements. And the cross-section of each pier was divided on some certain number of segments. And these segments are represented in this model with some springs, having some stiffness, and these springs are connected with rigid connections. I will talk in details later about the concept of the element and how the properties of this element should be defined. Before that, I would like to present you some history. These kind of elements are using for a long time. The first version of this element was introduced by Japanese researchers. This is in 1983. This is some reference of these older versions. And then, for example, Italian researchers also developed their version of this element. And finally, in 1992, at our faculty, Professor Fischinger, first of all, and Professor Pfeiffer with our colleagues, Tomasz Vidic, they presented the first version of this element. And it was the first application of this element was during the analysis of very well-known experiment in of Tsukuba building, which consisted of some frames and the wall in the middle of the building, and this specimen was excited in the direction of the wall. So this element was used to model the wall, and this was a 2D model. Actually, beside the MVLM, also the standard beam model with the Keda hysteretic rule was also applied. And here we have some displacement response history recorded during the test, and the results of analysis using multiple vertical line element and beam model. And what can be observed that the displacement obtained with the beam model were a bit smaller than the one with the MVLM. All over the height of the wall here we have the envelopes of the displacement, and we can see this line represent the displacement obtained by the standard beam model, and this line are the registered displacement and obtained with MVLM, and we can see that this model was better, first of all, because it was possible to take into account a very large uplift of these boundary columns, which was not possible to model properly. Well, the match with the experiment was also not very bad with the standard model, but much better with the MVLM. So this first version of the model was available in the Drain software, and as I already mentioned, it was developed and then we will see extended with the research team. The leader was Professor Fischinger. So what are the basic properties of this element? They are similar as this element is similar as other versions. Well, as I already mentioned, the cross section of the wall is divided on a certain number of segments, which are represented with this springs here, and it is typical for such a kind of elements. But the main difference regarding the rest of the elements of the same type is that the response of these springs is not defined by a stress-strain relationship, but a force displacement relationship. So the behavior of each of these springs is defined with some hysteretic rules, which are represented here and are described instead of stress-strain relationship with the force displacement relationship. It is also typical for these elements that we have also one horizontal spring, which defines the shear behavior, which can be described either by as an elastic response, or it can be also defined as a more complex response, which is defined on this figure here. But again, the relationship between displacement and the forces should be defined. How was the shape of these hysteretic loops defined? Based on the experiments, based on the observation of results of the experiments. So this is the main difference regarding the rest of the elements of this type, and regarding also this element which is already included in the original version of OpenSea. It's available on UC Berkeley site. So later, as I already mentioned, the first version was included in the Drain software, but later in 2005, it was included to OpenSea in our local version. And then it was also extended to 3D version to be able to perform also 3D analysis. This was the first extension, and in 2011, the more complex version was defined, which enables the coupling of axial shear flexure interaction to take into account. The versions that I already mentioned before, they don't have a coupled flexure and shear response, and this last version enables also this, and 2D and 3D versions are available of this model. First, in this presentation, I will first explain some basics of 2D element, how the stiffness matrix looks like, how we define the input parameters, and present the commands in OpenSea, how the element should be defined in OpenSea. And then I will present some basic features of the rest types of this element that I already mentioned. So this is the stiffness matrix, which is defined in a local coordinate system represented here. X-axis in the direction of the wall, so it is typically vertical, and Z-axis, which is used to define the location of these springs. And this element has 3 degrees of freedom in a local coordinate system, elongation in the direction of the element, and 2 rotations of the one and the second node. So what is, the stiffness is, are the forces which are produced by the initial, the unit elongation and the unit rotations. So in this way, based on the definition of the stiffness matrix is derived. For example, if we move this springs uniformly for one in the direction of the wall, then the forces in each springs are the same, and they are the stiffness, axial stiffness of the spring, and the sum of these forces represent the first element in the matrix. And then we can calculate the moments due to this displacement and so on. You already know how the stiffness matrix can be formed. But what I would like to say that beside this influence, we have also some additional parameter here, which represent the influence of the shear force. When we rotate, for example, this node here, we have also some horizontal displacement, which is equal to 1 is rotation. C is the distance of the shear force from the node, and L is the length of the element. So this is the displacement, and based on this displacement, we can calculate the force, multiplying this displacement by the shear stiffness, and then this force produce some moment also around this node, and this is this value represented here. So we have some shear stiffness included into the stiffness matrix, but the shear and flexural response are not coupled. So the properties are not changed. They don't have the influence of one to another. So this is the stiffness matrix in the local coordinate system. Then, of course, it is transformed from the local to the global coordinate system in a standard manner. Here is a transformation matrix. So this 3 degrees of freedom, then we transform everything to 6 degrees of freedom, which are typical for each analysis. And here is some general transformation metrics depending on this inclination angle of the element. But typically, this angle alpha is 90 degrees because the walls are typically vertical. So this is the typical transformation matrix taking into account that the walls are vertical. So the stiffness matrix from the local system is transformed, as I already mentioned, to the global coordinate system, and then the analysis is the same as for the other types of elements. But let's see how the behavior of these vertical springs is defined. I already mentioned it is defined with these hysteretic rules represented here on this figure. We have a special material named vertical spring type 1. And for each of these segments, I said we define one spring, and let's see what are the input parameters defining this behavior. The first parameter is the initial stiffness, K1, which is actually the axial stiffness of each element, which we can calculate as the area of each segment. So this area here, multiplied by modulus of elasticity of concrete and divided by the length of the element at the standard equation defining the axial stiffness. Then the next parameter is this force, F crack, actually the force when the concrete cracked, and we can calculate it as again the area of each segment multiplied by the concrete tensile strength. Then the yielding force, this is here we define the behavior in tension. So then we have the yielding force, which depends on the amount of steel multiplied by the tensile, the yielding stress of the steel. Then we have to define the yielding displacement, which can be calculated in this manner. Actually, the yielding force divided by the stiffness. And then the strain hardening, this is this branch, K3, which we have to define based on the properties of the steel. This is the behavior in tension, then the behavior in compression. In the first version, only the compressive strength force had to be defined simple in this manner, multiplying the area of each segment with the concrete compressive strength. And we have then some additional parameter presenting here alpha, beta, delta, gamma. I will explain it later, how we can define the unloading and reloading branch. Before that, I would like to say that in 2005, this vertical spring type 1 material was, the new one was added, vertical spring type 2 material, actually to be able to take into account the reduction of the compression, compressive strength, so to have the deterioration of the forces in this spring. So we have two possibilities. We don't expect the strength to be deteriorated. We can use the first model that I showed. If we expect this, we can use this vertical spring type 2 element. In that case, we have 3 additional parameters defining this branch. And for both of these materials, we have to define, as I mentioned, these parameters. Alpha parameter define the range of this unloading stiffness, okay, the second. Typically, this alpha is equal to 1, so it ends here on the axis. And then parameter beta defines this unloading branch. You can see it is defined by this force, which is defined based on the yielding force. And then gamma defines how this reloading branch, if it is 1, then this branch will go to the maximum displacement obtained in the previous cycle. But typically we use a bit larger value. This was observed in the experiment. These values are typically used for the analysis, but can be changed. And delta define this second stiffness regarding this one, the push. So to define the behavior of vertical springs, we have 2 types of uniaxial material, which is defined in a similar manner as other materials in the opposites. And then for the horizontal springs, spring 1, I mentioned that we can define the elastic behavior, or we can also this actually elastoplastic behavior, where we have to define the yielding force, actually the shear strength of the element, and the corresponding displacement. and then to define some deterioration parameter using this alpha parameter, which is typically 0.5. Also the print parameters are defined. We can print the internal forces at both nodes, then elongation and forces in the horizontal or the vertical springs. This is very important to control the response of the element. Then we can request the control of all these groups of data by command all, and also we can demand the data about the stiffness matrix, which is formed during the analysis. There are some additional parameters also, but they are not used very often. So these are the most important parameters that can be printed. So this is the element, this is the command in OpenSys, which is then used to define the element, the 2D version of the element. And it is very similar as the commands for other elements. First, we have to define the element tag, then the initial, the first, the second node, and then the uniaxial material of the horizontal spring. These parameters C I will explain later. And then in these brackets, we have a group of data. The first one is the coordinate of the vertical spring, and then the material, which is which we would like to join to each spring. So here we have to write the data for all springs that we have, for all segments actually that we divided the cross section to. The number of the segments is optional as much as we need. So this is then the last parameter that I have to explain is the parameter C. Probably to go better just to remember you that go back just to remember you why it is important. It is the position of the shear force in the element, and it is typically placed at the curvature centroid, and it depends on the moment distribution. If the moment distribution is linear, typically this parameter C is around 0.3. And if we assume that the moment distribution will be almost constant, then these parameters are 0.5. How we can know what to use? Actually, if we have short elements, then this is a better approximation. We have almost constant moments, so we use the 0.5. But if we have longer elements, for example, if we represent the whole wall with one element, it is rare, but it can be used, then we can use 0.3. So we have to decide based on the length. So this was a 2D element. 3D element is similar, but in the local coordinate system, for example, instead of 3, we have 6 degrees of freedom. Again, the rotation in both nodes, elongation, and the one which is added is also the torsional rotation. And the command to input the data is similar as for 2D element, but we have to define 2 materials for the horizontal spring. We have two of them in each direction, and one for the torsional spring. The parameter C is still used, and then when we define the vertical spring, we have to define two coordinates instead of one, and of course to define the material of each spring. And the last version, which was developed in 2011, I said it enables the axial shear flexural interaction. I will not going into details for this element because it is a more bit complicated than the previous two versions, but we'll explain only the basics. So here, instead of one shear spring, we have more springs, one corresponding to each vertical spring. And the behavior is defined taking into account some basic mechanism of shear response. Actually, the aggregate interlock, the dowel effect, and the effect of the shear reinforcement. So they are connected in parallel, and then they define the shear stiffness of each of this spring. There are some basic assumptions that were taken into account when this element was developed. So the problem is quite complex. And since this element is still force displacement based, some assumptions should be taken. It is assumed that all the cracks are strapped, so it is not possible to take into account such a different inclination, but the cracks are straight. And it is assumed that all the tensile and the shear deformation are localized in the cracks. And the inclination of the cracks is assumed to be the same along the total height of the element. And this inclination of the cracks is time array. And it is defined based on the average strength in the element following the inclination of the compression diagonal which are formed in the element. So how these horizontal springs can be defined? There are some relationships which are reported in the literature, and here we have some references which can be used to define the properties of interlock of aggregate. These two models, I recommend the Priestley model. It is, in my opinion, more appropriate. Then the dowel effect of the vertical reinforcement. Both of these references are okay, and the horizontal reinforcement, the effect can be modeled using the model of Elwald and Miele. For those who decide probably to try this element, here are more details about these references. So how can we model actually these contributions in open seas? Typically, we use the hysteretic material, and these are some examples that we used in some case studies that I will show a bit later. So, again, since this is quite complex element. I will not go into details because then I will need 40 minutes only for this element because the behavior is defined by the number of cracks, the maximum inclination angle, which demands both demand more explanation. And if you will be interested, we can send some more information about this. And probably now I can show some case studies. For example, this is one experiment very well known, performed at the University of California in San Diego. 7-story cantilever wall tested on their shake table. This is that wall, and it is important that there were some gravity columns here, and the one perpendicular wall to stabilize the whole specimen. So we used here in it was allowed the specimen to uplift. There was some slack, and in between the wall which was tested and this perpendicular one, there was a slab with some slots. Here at the slots, the slab was only 5 centimeters thick. So we used a 2D model, but we noticed that this slack was not enough, and it was closed. And here, the 4 different excitations were performed at, different intensities, and we noticed that the slack can be closed. So we decided at each story to add some springs to model this closure. And because of that, we got very good response. And our prediction actually was the best of all. So one additional thing that was necessary to do was to define this strain hardening of which was depended on the strain hardening of the steel. But in the beginning, we didn't know how much will be that. We took into account first this one corresponding to the maximum deformation in the steel, but later we noticed that the displacement which were obtained were much lower, so we increased the strain hardening accordingly. So as I said, the prediction was very good. These are the displacement envelopes at the first excitation and the last one. And we can see that it was quite a good prediction. The maximum accelerations and the residual displacements were also predicted quite good. But the forces were not so good. And I mean, at the top, it was okay, but in the first 3 stories, the discrepancy with the experiment in the last excitation, and the first excitation when the response was elastic, it was quite okay, but in the last excitation, it was a larger discrepancy was observed. And the main reason was this slotted slab. No one expected such an interaction between this perpendicular wall and this one which was tested. And it was observed, in spite of that, that the thickness of the slab was only 5 centimeters. And at these two places, the interaction was quite important. And that is why we obtained this difference. This was the test of the 2D version. Then we used this experiment actually because of this experiment and corresponding analysis, we developed the 3D version of the model. And here we have two T-shaped piers, wall piers, which were connected by beams in the slabs. Here is the specimen. The purpose of this experiment was to test the response of different reinforcement and the boundary columns. These walls were thin. They were lightly reinforced. In the boundary elements, we used different kind of transverse reinforcement, one according to Eurocode, one according to the older practice in Slovenia. And we actually expected the flexural behavior and failure of these walls. But surprisingly, what we got, and we also expected the damage of these coupling beams. But you can see from this figure here that we obtained the shear failure. What was the reason for such a behavior? You can see that these slabs are quite thick. And because of that, we got very strong coupling of the piers. And because of that, these two piers responded as one cross-section, not as two piers. And since we had also some additional masses here, the strength of stiffness was really large. Nothing was happened with the coupling beams, and the walls failed in shear. Locally, we obtained some damage in lightly reinforced corners without enough stirrups. The corners which were properly reinforced, there was no damage. So the model, each pier we modeled with beam column elements. At the places where we expected more damage, the elements were shorter than in upper stories. We used the longer elements, and here you can see how we divided the cross-section on the segments. These both piers were modeled with a similar model, and then they were connected with the coupling beams. Then the model of the coupling beams was, as I showed, for the horizontal springs in MVLEM. It can be used also for other purposes. And different kind of failures were considered when the strength of the coupling beams was defined diagonal reinforcement, then standard truss model for the shear in a concrete, then the strength defined by the failure mechanism, and the minimum was taken into account. And then if we compare, this is the response obtained by experiment, this gray bold line, and the black one represent the results of analysis, and you can see that they are quite poor. Why? Because we didn't have the proper model of the coupling beams. Actually, in the model, we got the failure, a very significant damage of the coupling beams. And you can see because of that, the coupling of the piers was lower than it was exactly obtained, and the period of the structure much longer. After the experiment, we changed the model, we improved the model, and since there was no damage of the coupling beams, we increased the strength, and you can see the response was much better. And finally, when we allowed the inelastic shear behavior of wall piers, we obtained a pretty good match with the experiment. So here, the model, it was not the problem of the model of the piers, but of the coupling beams. So this is the second, then we used the same experiment to test also the 3D MVLM model, but shear model when where the shear and the bending was coupled. And this is the fifth run in this experiment. We performed 6 runs, which were most of them biaxial excitation. And in the 5th run, we obtained pretty good match with the experiment. Of course, in this case, we already knew that there was no damage in coupling beams. But we can see here, if we analyze these contributions of different mechanisms to the shear response, that in this 5th run, where we obtained some damage, the main contribution was of the interlock of the aggregate, while the dowel effect and the shear reinforcement was activated, but there was no yield. In the 6th run, it was changed. The aggregate interlock was totally exhausted, and the dowel and the shear reinforcement were activated. And we can see here that the shear reinforcement contributed the most to the strength. The match with the experiment was good to the 3rd second, where actually the failure occurred in the experiment. But after that, the model was not able to follow the results of the experiment. And actually, it is assumed that here we don't have the clear sign of failure, because still the model behaved like a frame, which was not able to model in the analysis. So these are two case studies. Can I show a quick the other cases which are interested, or I can stop now?
No, please go ahead.
Thank you, because it is 45 minutes. Well, these are interested examples. We participated in the Wall Institute, which was organized to research different in different aspects of the seismic response of reinforced concrete walls. So these two, we studied different kind of walls, and these two examples are interesting because in these two walls, there were a very heavy, there was a very heavy reinforcement in the boundary columns, which was not typical for the walls that we already tested before. So here we tested the 2D MVLEM shear element, and it was necessary to change a few things. First of all, this vertical spring type 2 was not enough in this case, since on the compression side, the reinforcement had a very significant influence, and in such a cases, this material is not appropriate. I mean, the use of only this material, and we added this Meneotto Pinto steel model to represent the response of steel, and we coupled these two materials to obtain the actual one which was observed in the experiment. So what I would like to say that when you are using this MVLEM element, it is not necessary to use only the materials that we that we developed to be used by this element, but you can use any type of the element which is included in the open season, which is appropriate. Then for the inner springs where the reinforcement, there were only few bars, we used this vertical spring type 2. But what was the problem? In some inner segments, the crack force was larger than the yielding force. And in this case, the model can experience some numerical problems, which can be solved in a way to reduce the crack force to yielding force. That means that in this range, we'll not have the exact results, but since we typically are interested in a very nonlinear response, this is not quite a large problem. So the results were quite good when we changed the model of the boundary springs. The very good results were obtained. This is the envelope of displacements. The test was cyclic, so these are different levels of imposed displacements. And what is interesting that the flexure as well as a shear contribution to this envelope was very good catch. As well as the shear behavior. And this was the one of very rare elements which was able to model this, the strength deterioration in a shear. What I have to notice here that MVLEM models in general are very good in predicting the global response quantities, but it is not very good when the local quantities are analyzed. And these are the vertical strains. The solid lines represent the values obtained during the experiment, and this dashed line, the values which are obtained by the analysis. And at the strong excitation, we can see that the discrepancy is quite large. So to predict the strains, the element is not very accurate, but there is also one reason which is the problem also in other elements. And we can see that the Bernoulli hypothesis is not appropriate anymore in the walls. And this is the problem that should be solved in general. And then probably this is the last example. The last one, which was performed a few months ago, and my colleague Antonia Janevski, he's also present now. We modeled the e-defense buildings, which was tested at the e-defense center. The 10-story building was tested in a full scale. I think you had some presentations about this test before. And well, this building consists in one direction, it is a dual structure consisting of the shear wall. The first 7 stories, there is a shear wall and some columns and beams connecting. And in the upper 3 stories, we have a frame. And we modeled this shear wall using the standard MVLEM element, not shear, but standard. And what is interesting here, because we have a rectangular cross-section, to use the 3D model, we had to divide this cross-section not in one direction, but also in another one to 2 segments. And we obtained quite good results. Here, I have to notice that it was very important, this coupling. Well, they are not coupling beams, but beams which connect the wall and the columns. Again, the effective width of the slabs was a very important parameter, which defines the overall response. So in the upper stories, the effective width was obviously larger than in the first 7 stories. When we noticed this, we obtained quite good results in a global term. This is the hysteretic behavior, acceleration, displacement response in all 10 stories in the wall direction. Also, the envelopes of the displacements and the rifts was reasonably good in the analysis. And even some local quantities as well, rotation at the top of some stories was matched reasonably good, but displacement, the values of the rotation was a bit larger due to the problems that I explained earlier. So in the end, what I can say that as I already explained, different versions of this element are available in OpenSys, but only in the local versions of at the University of Ljubljana. In my opinion, this is relatively simple and robust macro element, and It can provide a variety of different modeling solutions. You can use different materials to define the response of the springs. And as I already demonstrated, if the input parameters are defined properly, the global response quantities can be simulated quite well. But it is less efficient if we are interested in the local response quantities as, for example, deformations in the tensile rainbows. Thank you very much for your attention. I hope.
Thank you for the presentation. Yeah.
Thank you.
Yeah. And I mean, does anyone have any questions? I mean, please feel free to ask. They take time to start. Oh, Professor Scott is also here today. So, yeah.
I guess that's a challenge, Pavan.
Yeah.
But yeah, I do have a couple questions. Tatjana, nice presentation. So we've seen a presentation a few months ago in this group on similar elements. Have there been any comparisons between that formulation and this formulation in terms of kind of relative accuracy compared to some of the experiments you showed? Or
you mean
from Christian Kalsvari and John Wallace group? Yeah.
Sorry, you mean this model that we showed the e-defense?
Yeah, so there's some
it
other.
It is actually the same model as I showed before. Probably we didn't have time to go into details at that meeting. So this is a more precise presentation of our model.
I mean, the model by Christian Kalsvari and John Wallace, like if there's been comparisons between that element and your element.
Models.
Yeah. But I mean, they kind of serve the same purpose.
Stress strain based. And our model is force displacement based. And it is a big difference. For example, what can be modeled here? As I mentioned in the previous meeting, I mean the e-defense meeting, that we didn't perform, for example, the analysis of this isolated building, which was, I mean, the test was performed before this classic building because we were able to take into account the initial pre-cracking. And it is very simple to define this reduction because simply it is possible to go back to the beginning. It is simple possible to reduce this K1 stiffness, and that's it. So
yeah, I guess
that is one thing that it is different.
Yeah, I mean, I guess my question is more like, given that these elements or formulations may be different or are different, has there been any comparison of the results, the simulated results, using these two elements? I mean, the other element formulation is.
Yeah, the comparison, there is a comparison. I didn't show the references. Let me go to the end of the presentation. During the Wall Institute, we performed the analysis of different types of walls, and some comparison is provided here in this paper. And there are some differences.
Sure.
These are 2D. Let me show this on this model. there were differences in the response. First of all, this shear part. So it was different. You can well, in this particular case, it was easier with this model to define the deterioration because, as I mentioned before, we have.
I mean, but you know the test results, right? So I mean, I guess it'd be good to see that comparison. But I guess in the interest of time,
sorry, I don't have the results here now, but
yeah. I'll go to. Can I ask a second question?
The original MVLM model in the OpenSys, it was not possible to define this degradation so simple because of the stress-strain relationship, and here we could define that reducing the. Let me. I don't have the results here.
All right. Well, I guess
it was possible to simply define the degradation of the parameter here. The Dowell effect was the most important, and it was possible to define this degradation, and that's how we obtain the proper response.
Okay, so second question. Thank you for the answer on that. Is at what point did I mean, this element that you've created is not available on OpenSys on GitHub, right? It's only available locally. So how does one, if anybody on this call or anybody who wants to use the element after they see the recording wants to use the element, how do they go about obtaining these special versions of OpenSys that have your elements?
Who is interested, we can send our version.
Okay, so then how old is that version, or at what point?
This for our analysis.
Do you keep the rest of the code updated with OpenSys? And do you check out the latest GitHub code for OpenSys?
We don't have these elements in the latest version of the OpenSys, but we plan to do that.
But I mean, the versions that you have.
That we included, it was 2.0. Antonio will know better which one is currently the last one.
It's on 3.2.2 now, right? So I mean, it's been some time since this kind of branching or forking of different versions has taken place. So I guess my question is, like, if somebody wants to use these elements, they're probably going to be using an older version, perhaps much older version if it's 2.0 version of OpenSys, right? And that in and of itself is going to cause problems.
Yes, right? I know, and that is why we plan to include it into the last one.
Okay.
So. Okay. But because really the last one has a lot of opportunities, different opportunities for modeling, but it takes some time, so we cannot. But
I mean,
change
it
takes all the time.
It takes time for everyone, right? I mean, everybody's adding their elements into OpenSys, the main GitHub repository, and so that other people can use it easily, right? So it's worth the time, I think. So
yeah. But well, we already talked about Antonio is ready to do that.
Okay. So. Okay. Well, I can help with that whenever the time comes. Send me an email. So.
Okay, thanks.
But thank you.
If you would like to use this older version, everyone who would like to test it, we can send.
Yeah, but it's going to have that element, but it's not going to have like 5 other things that people want to use, you know, that have been added since 2.0, right? So it causes issues, right? So
yeah, I
okay.
agree. But
yeah. Okay.
We need some time to do that.
Okay.
Thank you. Any other questions?
For the questions.
Yeah, we have some. Ali, you have any question?
Yes. Hello.
Yeah.
I have a question. Can you hear me?
Yeah, sure.
Hello.
Okay. I want to know, is it possible to combine your model or your elements with the direct differentiation method previously implemented in OpenSys for reliability analysis?
I didn't understand quite well. What did you ask?
Is it possible to combine your model, your elements with direct differentiation method DDM previously implemented in OpenSys?
No.
Okay, thank you. Thanks for your presentation.
Any other questions? I know a couple of wall guys here. So any other questions? Looks like no questions anymore. I mean, I had those two questions which Dr. Scott asked, so I was about to ask the same questions if they were available and all those, but yeah.
Okay.
Yeah, I mean, if there are no questions, then we will end the session here. Thank you so much, Professor. It was really helpful, I think. And yeah, hopefully we will see these latest versions available for everyone soon. Figures.
Thank you very much for your invitation. And I hope I fulfill your expectations.
Thank you. And have a good night and for you guys, and stay safe. Stay safe, everyone. Thank you for coming. And yeah, have a good day.